Solve for integers x and y. X cubed minus 5xy, plus y cubed, equals 2023. This is a Diophantine equation. There are two variables and one equation. So there might be more than one solutions. How to solve this equation? Usually there are different ways to solve this kind of equations. For example, one way might be to convert the equation to the product of two algebraic expressions of variables of interest equals a number. Due to the variables are integers, so each algebraic expression is an integer factor of the number. This leads to a system of equations. Then solve the system of equations, and find the integer solutions of the original equation. Another way might be to divide the problem into different cases, and narrow down the possible ranges of variables of interest. Then find the integer solutions for each case. For the given equation, clearly x times y cannot be equal to 0. Because 2023 is not a cube number. And xy cannot both be negative, otherwise the left side of the equation is negative, but the right side of the equation is positive. In addition, as the equality is symmetric about xy, so if xy is a solution, then so is yx. We know that a plus b all cubed equals a cubed plus b cubed plus 3ab times a plus b. By applying this, x cubed plus y cubed on the left side of the equation can be written as x plus y all cubed minus 3xy times x plus y. So the equation can now be written as x plus y all cubed minus 3xy times x plus y minus 5xy equals 2023. We divide the problem into different cases. Case 1. Both x and y are greater than 0. Rearrange the equation by moving terms containing x times y to the right side of the equation, and moving 2023 to the left side of the equation. The two terms on the right side of the equation have a common factor of x times y, so they can be written as xy times 5 plus 3 times x plus y. We know that x squared plus y squared is greater than or equal to 2xy. Add 2xy on both sides of the inequality. X squared plus y squared plus 2xy equals x plus y all squared. So we can now write x plus y all squared is greater than or equal to 4xy. Thus, xy is less than or equal to x plus y all squared over 4. So x plus y all cubed minus 2023 is less than or equal to x plus y all squared over 4 times 5 plus 3 times x plus y. Now multiply the inequality by 4, we have 4 times x plus y all cubed minus 4 times 2023, which is 8092, is less than or equal to 5 times x plus y all squared plus 3 times x plus y all cubed. Rearrange and simplify the equation, we have x plus y all cubed minus 5 times x plus y all squared is less than or equal to 8092. This inequality contains x plus y all cubed and x plus y all squared. We can evaluate the possible range of x plus y. Clearly, x plus y must be less than 30. When we substitute x plus y equals 22 in the left side of the inequality, we have 22 cubed minus 5 times 22 squared, which is equal to 8828, which is greater than 8092. When we substitute x plus y equals 21 in the left side of the inequality, we have 21 cubed minus 5 times 21 squared, which is equal to 7056, which is less than 8092. Therefore, x plus y must be less than or equal to 21. From equation 1, we know that the right side of the equation is greater than 0, as both x and y are greater than 0. So the left side of the equation must be greater than 0. So x plus y all cubed must be greater than 2023. We know that 12 cubed is 1728. and 13 cubed is 2197. Therefore, x plus y must be greater than or equal to 13. So x plus y can take values 13, 14, until 21. Substitute each of these values in equation 1, we find that, only when x plus y equals 19, x times y is an integer, which is 78. So we now have a system of equations, x plus y equals 19, and x times y equals 78. By the Vieta's formulas, x and y are roots of t squared minus 19t plus 78 equals 0. The left side of the equation can be factorized and written as t minus 6 times t minus 13. So either t minus 6 equals 0, or t minus 13 equals 0. That is, either t equals 6, or t equals 13. So x equals 6, y equals 13. Or x equals 13, y equals 6. Case 2, x is greater than 0, and y is less than 0. Note that, as x and y cannot both be negative, so the remaining case is either x is greater than 0, and y is less than 0, or x is less than 0, and y is greater than 0. As the equality is symmetric about xy, so we only need to consider x is greater than 0, and y is less than 0. If x plus y equals 0, then from equation 1, we have 5xy equals negative 2023. Clearly, it has no integer solutions. So discarded. If x plus y is greater than 0, then from equation 1, we have x times y equals x plus y all cubed, minus 2023, over 5 plus 3 times x plus y. Since x plus y is greater than 0, so the denominator is positive. As x times y is less than 0, so the numerator must be negative. That is, x plus y all cubed must be less than or equal to 2023. We have already known that 12 cubed is 1728, and 13 cubed is 2197. So x plus y must be less than or equal to 12. Also, as x plus y is greater than 0, so x plus y can take values 1, 2, until 12. Substitute each of these values in equation 1, we find that there are no integer solutions for x times y. So discarded. If x plus y is less than 0, then the left side of equation 1 is less than 0. So the right side of equation 1 must be less than 0. So we write 3xy times x plus y, plus 5xy, is less than 0. Note then the two terms have a common factor xy, so we can now write xy times 3 times x plus y, plus 5, is less than 0. Because x times y is less than 0, so 3 times x plus y, plus 5, must be greater than 0. That is, x plus y is greater than negative 5 over 3. Also because x plus y is less than 0, so x plus y can only equal negative 1. Substitute x plus y equals negative 1, in equation 1, we have x times y equals negative 1012. So we have a system of equations, x plus y equals negative 1, x times y equals negative 1012. By the Vieta's formulas, x and y are roots of t squared plus t minus 1012 equals 0. This equation has no integer solutions. So discarded. So in summary, there are only two sets of solutions. X equals 6, y equals 13. Or x equals 13, y equals 6.